Okay, I am going to walk through a biology slash ecology example of a nonlinear autonomous system of differential equations. Um, you should have already seen one example. Um, this one, it like the other one, fits contextually, and we're going to talk about that a lot as we go through here. I have 15 minutes here. We'll see if I doubt there's no way I get it into one go. So we'll see how many videos this takes. Okay, so um, we first off want to talk about what an autonomous system is. Oh, one, I did this on graph paper on a notebook, so that it is what it is. So I apologize if it's a little bit hard to read, but you should be able to um, see what's going on as I walk through everything. Anyway, autonomous means there's no t's on the right hand side, and linear. You should understand all the ones that we did previously with eigenvalues and eigenvectors. In our first go around with this, those were all linear. Um, I'll have an example down later of one that's linear. So I want to take an example where x equals the species number one, its population size, and then y is another species population size, and they interact with each other. But before we do that, I want to look at two old problems of ours. dp dt equals k times p with a positive k. You should know all the work for that. You should be able to do it in your sleep. That gives us poked, which is an exponential growth model. The other one that was really similar to that, you had to use some partial fractions and some like sort of intense algebra to get the solution to this one. But it was dp dt equals k times p times a number minus p. I just put 500 in there for kicks. Um, this is logistic growth, and that 500 is the carrying capacity. I don't know the equation for that, but really what I care about is this graphic representation of it. We figured out way back when that it would start low and go up and then over. And I could even draw one here, like say it started here, it would go up and then flatten out. Um, and if it was above there, if it was above the carrying capacity, then the population size would dip down to the carrying capacity because there'd be too much in there, right? Um, and you could work all that out. That's not what we're doing here. I think we did that in the beginning of this year. What we're gonna do with this species one and species two, remember x is the population size, y is the population size. So come down here, I got this example, x prime equals this, y prime equals this. Notice that's the derivative with respect to time. So that's the rate of change of the population size for each of these. So I'm just going to inspect some things for x prime. Um, and I think you'll see how it relates to the stuff up here. So I got x prime equals 14x minus 2x squared minus xy. This minus xy, that is the interaction factor here. It's the interaction rate. This is a rate. This is how the rate is changed by interaction because it's got x and a y. Think about it. If x was really big and y was really big, then the two populations would run into each other a lot, so they would see each other a lot. If x was big and y was small, they would run into each other less, so this factor would be less. If x was 0 and y was anything, they wouldn't run into each other because this term would be 0. So that's the interaction rate piece of this. Notice it's got a negative coefficient out front. So that tells me that these guys kind of compete with each other, or that basically if there is that interaction between the two of them negatively affects the size of X's population. So the way to interpret that um, contextually is that this species X is either a prey, that Y is the predator and X is the prey, or they just simply compete for space with the Y species. So then we can, the other thing that I can do to look at, so like that's the interaction part of it. So now what I'm going to do is like think about this problem and say, well, what if I just got rid of that? What kind of system would I have? What would be going on with X, right? So if I just get rid of that interaction term and see how see how x would act all by itself, then I get x prime equals 14x minus 2x squared. That's just these two terms right here. Notice I can pull the 2x out, and look what I get. See, boom, just enough space. This right here is x prime. It's dx dt. And then 2x times 7 minus it's kp times 500p. It's the same form as this. So this would be, if there was no interaction rate, x would be a logistic growth model, or it would have a carrying capacity of, in this case, 7, right? So my conclusion, and I do this because, look, do you see that everything that I looked at there, if I were to have done it for y, I would have said all the exact same things, except for the 14 would have been a 16. My conclusion is that both x and y have some sort of logistic carrying capacity, and that they both either, it wouldn't make sense for them both to be praised for each other, so maybe it's some kind of competition for space. So let's go down. All right, so the first thing I need to do, that was me here just kind of laying out the problem. What's an autonomous system, and what the heck is going on here in this context, in this population model context? So let's talk about actually solving the problem now. So the first thing I need to do is find the critical points. Remember from the last example that this is where both x prime and y prime are 0. So I'm taking this guy right here and making that a 0 and that a 0. Like that. There are 4 critical points for this system. So the first one is, sorry, I should say, once I got this, I generally try to factor these things. They don't always factor. Sometimes you got to use other ways, brute force, to figure out when they're all 0. But for the most part, these predator-prey ones that we work with, you can do this factoring system that I'm doing here. So look, the first way that I can make this system of equations true is if that and that were both 0. Because if this was 0x and that was 0, then they would multiply by whatever it is over here. It doesn't matter, and it would make this system true. So 0, 0, that should be pretty obvious to you. Then what I did, there's an arrow there that didn't really show up in my scan. The other one that I get is 0, 8. Now, let me show you how we get that. If this is 0, right? Then I know that the top equation is 0, and I don't have to worry about it. So if that x is 0, then the top is 0. If I've got x equal to 0, and I also want to make the bottom 0, well, I can attack that guy, which is what we did here, or I can attack this set of parentheses. Notice that if I make that 0 there, that I get 16 minus 2y, right? So if x equals 0, it makes x prime 0. That also makes a 0 right here, which gives me, if this set of parentheses to make that 0, I would go 16 minus 2y is 0, which gives me y equals 8. So I get 0, 8. So 7, 0 is the same. If I make the bottom equation by making y equal to 0, and then instead of looking at this piece, look at this piece, then that would be 0, and you should see that x equals 7 would solve that. So I've got 3 critical points so far, 0, 0, 0, 8, and 7, 0. The last one is a little bit more work, right? So let me talk about what I've done. I've done this with that, and then this with that. So I've gone down and across, and then up and across right there, right? So now I compare these two, right? If I want to make them both 0, then it would satisfy this equation. So come down here. The last critical point is the most work, but you should also see it here. So to make these guys 0, it's 14 minus 2x minus y is 0, and then 16 minus 2y minus x is 0. So this is a linear system from like algebra 1, and you should be able to solve that. You can solve this however you want. I typically just prefer to pump it into my calculator and use reduced row echelon form, RREF. Let's make sure I didn't mess this up. 2x moves over, this moves over, 2x plus y. These move over. Be really careful right there, right? Because look, these are not in the same order, right? This goes x, then y, this goes y, then x. So when I pop them over, this is the one that has the coefficient of 1, and that guy's got 2. So I get 2, 1, 14, 1, 2, 16. REF it, I get 4 and 6. So you could use elimination, lots of different things you could do for that. So our 4 critical points are 0, 0, 0, 8, 7, 0, and 4, 6. That was step 1. And I think I have 5 in this PDF. So that was step 1 of 5, but the rest of it kind of goes a little bit quicker. All right, so I think we can do step 2, and then we'll pump to another video. The next thing I do is calculate the Jacobian for this original matrix with partial derivatives. So F is the x prime equation, G is the y prime equation, and my Jacobian is F sub x, F sub y, G sub x, G sub y. The reason why I'm not doing x prime sub x is because that's like really confusing and terrible notation, right? So I think it's pretty standard to let one of them be f, the other one be g, and write the Jacobian like this. So you should be okay with your partials. The partial x of this, don't forget the power rule on this guy, you're going to multiply by 2. That gives me the -4. And then remember with this term, I'm treating y as a constant when I take the partial x, right? So when I do that, this acts like a coefficient. So the partial derivative is just a -y. And then I'm not going to go over all these, but your Jacobian is this. And hopefully you can see all them, and you should calculate all those and make sure you agree with me. So side note here, if you have taken or are in multivariable, then this operation should feel a little bit familiar. If you remember, we did the second partials test to figure out mins and maxes, and we looked at a D. It was a determinant. So I slapped determinant bars on here. This is the same matrix that we used, but F and G would have been the first partials, right? So if F here was the, I should have a different letter here instead of F there, maybe anyway, it shows up, this Jacobian shows up all over the place, and this like mixture of taking these partial derivatives shows up all over the place. So it would be like if I had a big F, if this was a big F and big F and big F and big F, and big F was a multivariable f of x comma y function, then if I were to calculate the partial x and then do the partial xy, I got partial xx, partial xy, and then do the partial y x, partial yy. Anyway, this should feel familiar. Anyway, I'm going to stop here, and we'll do the rest of this in another video.